on this misprint day, we're going to look at and define and use the inverse of the tangent function. And the nice thing about what we're doing today is essentially it's going to be the same as we've done before, just inverse of tangent. So in terms of strategies, I'm teaching you nothing new. Just new context is all. All right, you already did the warm-up there with the board leaning against the fence. And I do want to show you what the inverse of a tangent function looks like. And before we get into practical problems, let's just look at some common restrictions that we need to make on the domain. So when we found the inverse of cosine and sine, we did limit the domain of each inverse. So the same is going to be done for the inverse of tangent, and here's why. If we were to take a moment and graph the function tangent of x, what we get is a fun diagram that looks like that. Notice that there is a gazillion of these fun little squiggles. And just to use our lovely math terms, there are a gazillion asymptotes as well. Every single one of these red curves will approach but never hit this vertical line here, this vertical line here. So any of the vertical lines that fall what look like in between these ones here. So we do know that if we were to do this, we have an infinite number, which means if I were to attempt to rotate, or reflect, if we just show you here, that's what I just graphed right there, is this tangent here, tangent there. Now, if this is my line of reflection for inversing, notice what happens. All those little puppies there start to show up. This guy here is an inverse of tangent. This guy here is an inverse, and this guy here is an inverse. Except for the fact all three yellow there now fail the vertical line test, right? They fail the vertical line test. So what we need to do is limit the domain to just one of these horizontal-like squiggles, okay? So the question, of course, is which one of those is going to be it? And down here is the simple answer. We're actually restricting the domain to be the same as the previous one that we just did, the sine. So the inverse of sine has the same restriction as the tangent, the inverse of tangent. So we're just focusing here. Notice this is a line of asymptote right there and there, which means when we reflect it on x, y equals x, then we get those same asymptotes just horizontally. So there's our restriction of the domain. That's all we wanted to point out about that. Nothing new, nothing exciting. So when we define the inverse of tangent, of course, its simple definition is this. Tangent, the inverse of tangent of x, y is that if and only if x is the tangent of y. And again, here's our restriction of the domain. Again, don't forget that many times we will use arctan to represent tangent to the negative 1. Same thing. Again, like we said, nothing new here. So we're going to find the approximate value of each in radians. So all we do is plug this happy thing into our calculator. And in doing so, the tangent of radical 3 is 60, and I'm in degrees. So I'm in 60 degrees there. When you change your function, when you change the mode to radians and re-enter that, you'll get the radians version of that. The radians version of this one is very simple, actually. It's pi over 3, but right now you didn't know that, so many of you punched it in your calculators, got 1.045. Okay, so radians there. But it turns out that it's pi over 3 as an exact answer there. And what do we get for these ones here? So check your answer here. All right, so let's look into some application. Example number 2. A plane is flying at an altitude of 32,000 feet, which is about 6 miles up, and wants to descend to an airport runway X miles away at a constant angle. That is key. Because when an airplane descends, if he descends like this and then drops quick and then drops quick, obviously you're going to get a lot of people falling out of their seats there. So having a constant drop down is going to be a very calming situation. So, again, a diagram may be very helpful for this. So, the airplane is at an altitude of 32,000 feet, so we know that this is 32,000 feet right here. And then calling this the ground. And actually, this one is going to be more difficult to draw out, only because it's probably the blue there is probably going to be quite long. So in just doing my sketch here, I will not do it perfectly to scale. Okay, so remember what the angle of descent is based on. The angle of descent is based on the horizontal, right? So we're looking for this theta right here, folks. This theta right there. Which means, by parallel lines cut by a transversal, we're looking for this theta down there. All right, so x miles away is going to be the blue there. So this is my x miles. And I think I'm going to keep it into feet right now because 32,000 is an exact number because this one says about 6. And then I'm just going to divide by the 5,280 in a moment. So first the equation. So relative to this theta right here, this is opposite and that's my adjacent. So it's going to look like this. The tangent of theta is equal to 32,000 feet over, it says x miles, but I'll say x for now and let's do the conversion later. So officially it should be x feet for now, and then we're going to convert it. All right. So we're here told that x is 30 miles. So one of these I need to convert. Either I convert the 32,000 to a decimal by dividing by 5,280, or I multiply this by 5,280. And that, in actual fact, it's probably better to convert this one, so we're dealing with smaller numbers. So when I convert the tangent of theta and I convert to miles, 6.061 miles over 30 miles. And like we've done before with the other inverses, I'm going to do inverse of tangent on both sides. And all I have to do is plug this part into the calculator. And when we punch that into our calculator, we get approximately 11.42 degrees. Now it does say round to the nearest degree, so I'm going to go ahead and change that to 11 degrees. So there's my final answer, 11 degrees. Now let's look at the next problem together. Eddie is watching a skyscraper being built from her apartment building, which is 0.75 miles away. Here I rounded it, multiplied by 5,280 to get 3,960 feet away. Her third floor window is 25 feet from the ground. As the skyscraper reaches a height of h, so it's not simply this x here, it's the height of h. So what is the angle of elevation to the top of the skyscraper in terms of h? So relative to this theta here, which, by the way, if we were to extend down to here to the actual ground, down to here, theta would be congruent to this angle down here because of parallel lines cut by a transversal. Those would be corresponding angles. So theta is also down here. So that means theta is going to be the opposite, which right now is just h, over some other amount. So what we need to do instead is talk about it in terms of this right here, this x, and we're going to add the 28 degrees, or excuse me, 28 feet to it to get h. So we are going to use tangent because opposite and adjacent. We know that h is x plus 28, so x by itself is h minus 28. So opposite is x, or h minus 28. So h minus 28 all over my adjacent, which is 3960 feet. And so that's actually the answer for up here. And now, in order to find out what the angle is, we're going to use some more information. It does say that, well, what if we're told that it's 400 feet? Well, now we have this here, so we can plug that into our calculators and also do the inverse of tangent on both sides. And after a lot of fidgeting with the calculator, you'll end up with approximately 5.4 degrees. And there we go. So this is clearly not to scale because 5.4 degrees is a very, very thin angle right there. All right, so this is the extent of our work for the inverse of the tangent function. On page 3, there's another practice problem for you to work on. Enjoy.